All right, so I'm going to talk to you guys today about the impact of increasing rainfall and rain on snow on flood generation in a Canadian prairie catchment. So the hydrology of the Canadian prairies has been well described in the previous literature. About a third of the precipitation falls as snow, and the snow gets redistributed into channels and depressions on the landscape. So in the spring, snowmelt typically occurs over frozen soils, and this actually accounts for over 80% of the annual runoff in the region. Rainfall in the summer doesn't typically generate runoff as the evapotranspiration rates quickly deplete the soil moisture levels. So the runoff that is generated on the Canadian prairies drains into those depressions on the landscape, and this forms your isolated wetlands. And if the storage capacity of these isolated wetlands are exceeded, then these streams can connect to one another, wetlands can connect to one another or to streams. So this results in a dynamic contributing area for runoff and increases during times of high runoff, like your snowmelt period, and contracts in drier conditions, like in your summer, when it's a little bit drier. So here is a typical streamflow hydrograph for a Canadian prairie catchment. As you can see, streamflow peaks in spring during snowmelt and then recedes to zero flow for the remainder of the summer due to a lack of inputs. But things seem to be changing a bit. Recently, the region has experienced increased streamflow and flooding, as you can see with the 2011 and 2014 graphs. In 2011, massive spring flooding occurred across the eastern portion of the Canadian prairies, and then again in 2014, the streamflow peaked in summer, so we had a second peak occurring. So it was important to understand what changes occurred to cause these changes in streamflow characteristics. So I looked at the Smith Creek Research Basin, and it's located in southeastern Saskatchewan, Canada. It's a relatively small basin, under 400 kilometers squared. It's very much agriculturally dominated, so farmers in the basin have been draining wetlands for decades now to increase their agricultural production. So from 1958 to 2009, wetland extent has been reduced by 58%. The wetlands here, I should mention, are the red color in the figure, and the drainage channels that have been formed by the farmers are colored in blue. So we're seeing this massive loss in the wetland area in the basin. And when I'm talking about wetland drainage, this is kind of what I'm referring to. This is how it alters the landscape. These are photos taken within the Smith Creek Research Basin, and the photo on the left is of an area where no wetland drainage has occurred. And as you can see, that surface water that is generated is stored on the landscape. And compare that to the photo on the right, that surface runoff follows those drainage channels that have been formed and into the streams. So you have a reduced storage capacity of the landscape. So for this study, I gathered precipitation and temperature data from both Environment Canada and as well as the Centre for Hydrology, who had a meteorological station set up in the basin pictured here. Since I used a few different meteorological stations, that data needed to be adjusted for that spatial variability. And just to note that this data follows a hydrological year of November to the following October to make sure that proper snow season is in with the same streamflow season. And streamflow data records were taken from the Water Survey of Canada since the record started in 1975. And I'd just like to note that the 2014 data is preliminary. As Al mentioned, there's a little bit of a delay to get that adjusted data out. So that data is not quite available, but I'm still going to include it in the analysis because 2014 was a very interesting year. So to gain an understanding of how the runoff generating mechanisms have changed in the basin, I separated out the streamflow into the various runoff mechanisms: snowmelt runoff, rain on snow runoff, and rainfall runoff. So to follow through a few different rules that I've went through, streamflow starts, as you can see, with the blue as a snowmelt runoff regime during that snowmelt freshet. And it stays classified as such until either you have a daily rainfall greater than 5 millimeters that has to immediately increase your discharge of the stream, or else B, your streamflow ceases after your snowmelt finishes for the year. So if you get a situation where you have a daily rainfall and it increases your discharge, if that discharge is greater than 0.1 cubic meters per second prior to that rainfall, then it enters a rain on snow runoff regime, as you can see here in the graph, changes to a red color. If that discharge is less than 0.1 cubic meters per second, then it enters a rainfall runoff regime, as that snowmelt portion is deemed to be negligible. And then if streamflow resumes again after the snowmelt freshet has completed due to rainfall events, then of course it enters a rainfall runoff regime. So to get into some changes that we have seen in the basin, looking at annual precipitation, there has been no changes to the total amount of annual precipitation. But what we are seeing occurring is a phase change, and this is due to increasing temperatures that we've noted. So there's been a significant increase in the rainfall fraction of the precipitation and a decrease in the snowfall fraction. So this rainfall fraction has increased from 68% now up to 78% of that annual precipitation. So that's decreased snowfall amounts down to just 22%. And then when looking at a monthly time scale, you can see that March is found to be also increasing. We're seeing a quadrupling of the March rainfall fractions. And this is also due to increasing temperatures that we're seeing in that month of about a mean of 3.5 degrees Celsius since the early 1940s. So the March rainfall fraction is increasing from about 4% up to over 22% now of that monthly precipitation. So this is important to note because March is when snow is still on the ground on the Canadian prairies. So if you're increasing that amount of rainfall that occurs during that month, you're increasing those incidences of rain on snow events, and they can be responsible for massive flooding. So not only is a monthly rainfall fraction increasing in March, but also is a monthly rainfall amount. And then as I explained, March rainfalls can increase your rain on snow events. May and June is also seeing a pretty substantial increase of 28 and 34 millimeters respectively. And as well as October, we're seeing increases. And I'll get into how those have impacted the streamflow just briefly here. So, streamflow records, moving into those. Given those changes in land use and the climate, we're seeing that streamflow is responding to this. There's been a 14-fold increase in streamflow volumes, so from 3,000 decameters cubed up to now over 42,000 decameters cubed. So that's a substantial increase that we're seeing. And we're seeing increases from all three runoff mechanisms that I mentioned. So snowmelt runoff, we found, even though there's a decline in snowfall amounts, we're actually seeing an increase in snowmelt runoff by about 5-fold. And this may be due to those October rainfall increases that I mentioned, because if your soils freeze when they're wet, the snowmelt infiltration in the following spring is limited, so that can increase your snowmelt runoff. Rain on snow runoff, that actually increased 34-fold. So there's been a drastic increase in rain on snow runoff. And then rainfall runoff also, a 150-fold increase in the amount of rainfall runoff in the basin. So there's a lot of things going on. With rainfall runoff, it's most likely due to those May and June increases in rainfall that we're seeing, because that rain is following shortly after the snowmelt season ends. So the basin is wet from that snowmelt runoff. So if you're adding water to an already wet basin, that can increase your stream flow during that time. So not only are the contributions from the runoff mechanisms changing, but the portion of streamflow derived from each one of those mechanisms is also shifting. So as you can see, there's been 2 shifts occurring in streamflow, one in 1994, the other in 2010. So from 1975 to 1994, snowmelt runoff accounted for 86% of the annual streamflow volume. So that's well within the expected over 80% on the Canadian prairies. But since then, things have declined. Our snowmelt portions have declined quite a bit, down to now just 47% of that annual streamflow volume. Rain on snow runoff has taken a substantial increase up to 19%. And rainfall runoff, has increased from 7% up to 34%. So there's a shift going on here in the stream flow, because rain on snow and rainfall runoff portion of stream flow combined is now accounting for over 50% of the annual stream flow volumes, and that's drastically different than the 15% that the stream flow historically had. So there's been 4 floods that have been recorded in the Smith Creek Basin, and they're listed here. The first one is in 1995, and as you can see, it's very much a snowmelt-dominated flood event. 99% of the stream flow was from snowmelt processes. But shifting up to 2001, this was the largest stream flow on record for this basin in regards to volume. And during this flood, there was a massive amount of snow that accumulated over the winter months. And then while it was melting, large amounts of rain fell across the eastern portion of the Canadian prairies and caused massive flooding and cost hundreds of millions of dollars just in Saskatchewan alone. So as you can see here, there's still some snowbanks on the edge of the stream there. So stream flow, it was just crazy huge. So the gauging station, as you can see, is underwater, and somewhere underneath that whirlpool there is a culvert located. And then again in 2012, another flood occurred. It wasn't as big of a flood, but the interesting fact about this one was that it was the first ever rainfall-driven flood on record. So over 76% of the stream flow that year was derived from rainfall runoff processes. And as you can see in the picture, it's nice and green, looks beautiful. Growing season, farmers did not appreciate that flood. And you can see the culvert here now in that picture. And then again in 2014, another major flood occurred, and this one again was a rainfall-driven flood event. And the interesting thing about this flood was that this flood actually broke peak flow records. So peak flow now in this basin is derived from a rainfall runoff event that occurred in late June, early July. So to help you visualize how things have changed in the basin, these are the maximum, minimum, and mean hydrographs for the 3 different time periods that I separated out streamflow into previously. So during that first time period, as you can see, streamflow is very characteristic of what the Canadian prairies have been described to be. Snowmelt runoff and recedes to zero flow for the remainder of the summer months. And then things start to change during that second time period. You start to see an increase in streamflow in spring, and then it extends out into the summer months. And then during that last time period, you can see that not only are we getting a larger spring increase, but we're also seeing a second peak starting to show up in the hydrographs. So things are starting to change. We're starting to see that increase in rainfall show up in the streamflow. So to conclude, there's been no changes to the total annual precipitation in this basin. But due to those increasing temperatures, we're seeing an increase in rainfall show up and a decrease in the snowfall. And this is also prominent in the month of March. We're seeing an increasing rainfall amounts in March, May, June, and October, and this is increasing those incidents of rain and snow events, as well as an increase in rainfall shortly after snowmelt period, which can also influence the streamflow as we've seen. There's been a 14-fold increase in streamflow volumes, and we're seeing increases from all 3 runoff mechanisms in the basin, particularly 150-fold in rainfall and 34-fold in rain-on-snow runoff. So this increasing importance of rain-on-snow and rainfall runoff generation is important for floods, because we've seen these massive floodings, as in 2011 and 2014, from those 2 different runoff regimes. So most of this rainfall, or change in streamflow, is due to changes in climate, but the magnitude of the change may be influenced by that wetland drainage I briefly discussed. So the next step for this project will be to model those changing hydrological processes caused by the changes in climate and in wetland drainage, and especially the rain-on-snow floods, as it can cause massive widespread flooding on the Canadian prairies. Thank you.
We have time for 1 or 2 quick questions.
I am not 100% sure on that. I know Ducks Unlimited has purchased land to conserve some areas and those wetlands there, but to buy back, I actually am not unsure on that one.
With the increase in streamflow volume, but no commensurate increase in precipitation, would you speculate that that's a difference in evapotranspiration, or where's the mechanism for the increase in streamflow?
It could be the change in the increase in streamflow. Oh, slide's gone. Sorry, can you repeat the question?
Just water balance-wise, with an increase, a 14-fold increase in streamflow, but no change in total precipitation, where if you would account all that to evapotranspiration or change in storage? Or?
I don't know about evapotranspiration. It definitely is a change in storage, as you've seen, because there's been a 58% loss in the wetland area. So that's, a drastic change in the amount of water that can be stored on that landscape, and it's mostly heading into the streams instead. So that's mostly the change in storage that we're seeing, as well as the change in phase that we're seeing and the timing of that precipitation.